In this video, I just want to talk about a few different ways that you can determine what is the anode and what is the cathode in an electrolysis. In an electrochemical cell, typically a voltaic or a galvanic cell. So all of these examples will be examples of a voltaic or galvanic cell. So looking at this question right here, we can see that zinc reacts with cobalt 2 plus to produce regular cobalt. So that means cobalt's going from a positive 2 oxidation number to a 0 oxidation number. So therefore it is being reduced, and therefore zinc is the one that's going to be oxidized. Okay, another way that they give you information is down here. They give you the cell potentials, and remember that for a voltaic cell, that it must be a positive value. So you can either go negative 0.76 minus negative 0.28, or the opposite, negative 0.28 minus negative 0.76. And remember, it's cathode minus anode, or oxidation minus reduction. And we know that the cobalt was the one being reduced, so it does need to be this one. Okay, partially because we already knew that cobalt was the one being reduced, but at the same time, we also know because that's the one that gives you a positive answer. Okay, let's look at another one here. Again, right away, what's being oxidized and what's being reduced. So in this case, they don't tell you much. They do tell you it's galvanic, though. So remember, galvanic and voltaic are the same thing. So if it's galvanic, it has to be a positive cell potential. Okay, and I don't know if I've mentioned this yet or not, but the stoichiometry of the balanced equation does not affect the cell potential here. That's a very common mistake to make, because with like thermodynamics, enthalpy changes, Hess's law, it does change the enthalpy change. And with equilibrium constants, if you double an equation, you have to square the equilibrium constant. Okay, with cell potentials, you do not, the stoichiometry of the balanced equation does not change the cell potential. Okay, so the fact that this is a 3 and this is a 2, and you'd have to turn them both to 6, does not change the fact that it's 0.15 minus negative 0.74, and that's the only way that you're going to get a positive value out of that. So we know this one has to be the cathode, this one has to be the anode. So this is the reduction process, this is the oxidation process. Okay, and this one here, again, we're looking for clues as to which one's being oxidized, which one's being reduced. It says when the switch is closed, the mass of the tin electrode increases. Okay, and based on what we've learned about voltaic cells, remember you've got either Sn becoming Sn2 plus, and that's when the mass is going to go down. That's when this tin here is going to turn into tin ions, and that the mass of this piece of metal is going to go down. But an Sn2 plus becoming Sn, in that case, you're taking some of the tin ions from the solution and you are plating it onto the metal. That is the reduction process. That's when the mass of the electrode goes up. So if the mass of the tin electrode increases, that must be the reduction process, and that's the one that occurs at the cathode. Okay, let's look at another one here. This is probably the trickiest one I've ever seen. Okay, it says, it's observed that when silver metal is placed into aqueous thallium-1 fluoride, TLF, no reaction occurs, which means when you take Ag plus TL plus, I'm writing the net ionic equation there, I'm canceling out the fluorine. Okay, I get Ag plus TL is what I should get. But it says no reaction occurs, which means in this case, silver would be being oxidized and the thallium would be getting reduced. But if it tells you that no reaction happens, then that means that the silver is not going to be oxidized, and therefore the silver is going to be reduced. Okay, so if the forward reaction doesn't happen, no reaction occurs, but then they say when the switch is closed, the cell does produce a voltage of 1.14 volts. What does that mean? Well, if this one doesn't go, then instead of the silver being oxidized, then the silver is going to be reduced. And so Ag plus becoming Ag does happen, and TL becoming TL plus does happen. Okay, because the forward reaction doesn't go, then because when you close that switch, if silver can't be oxidized, well, then silver has to be reduced. Okay, and hopefully that will help you there with that question. On this one here, we can see when the switch is closed, electrons flow through the switch from lead to X. So the electrons are flowing this way is what it says. What does that tell you? It means that the electrons always leave the anode and go to the cathode. So that means this side here is the anode where oxidation is occurring. This side is the cathode where, not oxidation, where reduction is occurring. Okay, let's see. This one, just standard cell potential. The way that they're trying to trick you on this question is just to know that, again, the stoichiometry of the balanced equation does not affect the cell potential. You're going to have to triple this one here on the bottom to make those electrons equal 3. Okay, but you do not change these values do not change. So what's the only way to get this to a positive value is to take 0.80 minus negative 1.66. Okay, and again, that's the cathode, that's the anode, that's where reduction occurs, this is where oxidation occurs, and that's what happens. The Ag plus stays the same. Notice it's still Ag plus and Ag, but notice the aluminums are getting flipped. Okay, and again, that's what that negative sign does, is remember they're always written as reductions, and so going cathode minus anode without doing anything to these signs is how you're always going to do that. Okay, that one, nothing really tricky there. Again, as the current flows, the student determines that the copper electrode increases in mass. So if the copper one is increasing in mass, that means that the Cu2 plus ions are becoming solid copper. The copper's plating onto itself right here. And so that is the cathode where reduction is occurring. Okay, so if that's the cathode, then tin, therefore, must be the anode where oxidation is occurring. Okay, and I think this one's a really good example. I actually graded this one. This is back when we used to do the in-person grading. So I graded this question thousands and thousands of times. And a lot of times kids saw this 4 and the 12. And what did they do? They multiplied this number by 3. You don't do that, okay? You take the two values. How do you get, it's a galvanic cell, so how do you get a positive value? 1.229 minus negative 0.085, okay? And the correct answer was 1.314. This, remember, with addition and subtraction with significant figures, this has 3 after, this has 3 after. Your answer must have 3 after. This was the significant figure question, and I had to take off a lot of points because a lot of people put 1.31, a lot of people put 1.3. Okay, with addition subtraction, remember, it's how many come after the decimal point. Okay, and so those are just a few examples of some different ones where how are they giving you enough information to figure out what's the anode, what is the cathode when you're doing a voltaic cell type problem.